So I wanted to try something different. I wanted to record the notes ahead of time and let them be available for all students, especially if students were absent or had questions later, they could maybe go back and rewatch these. So this is the first time through. That being said, if you need to pause or rewind, please do at any time. Also, there are guided notes that go along with this. They should be in the comments, but if you were in my class, they will also be in the back of the classroom. Let's begin. So today we're going to look over velocity time graphs. This is our first lesson in the acceleration unit. So in these notes, we will review position time graphing. We will graph constant and changing velocities. We are going to define acceleration for the purposes of this class. We are going to practice what we have learned thus far. And the very last thing we'll do is find displacement from a velocity time graph. So recall that in the previous unit, we learned how to find our slope, which gave us velocity. So that was our rise over our run. And our rise, remember, is our position here. And our run would be time. So if we look at that, our slope is our velocity in meters per second. Oops, let me go back to this. In meters per second here. So let's say this slope is about 5 meters per second. What would the velocity versus time graph look like here? So we can start by having our graph with time on the bottom. Again, we know that time is still our x or independent variable. And now we're going to have velocity. And that is going to be in meters per second. I just ran out of room, but traditionally it'd be on this side. And looking back at this graph up here, at 1 second, what was the velocity? Well, that slope is the same all the way through, so it's going to be 1 meter per second, or 5 meters per second, excuse me. So that's 1 second. Actually, let me get the right color. 1 second, 2 seconds, 3 seconds, 4 seconds, 5. So now at 2 seconds, our velocity is still 5 meters per second, and we can see that it's all the way through. It's going to be 5 meters per second. So now I'm going to use a different color for this line, and we'll talk about why in just a moment. So these should roughly be in a line. Freehanding this is a little bit off. So So my screen seems to have frozen up. Let's see if that gets it back. There we go. So then at 3 seconds it was here. Let's highlighter. Here, 4 seconds it was here, and 5 seconds it was here. So that being said, We know that all position time graphs that have a linear or direct relationship will produce a velocity time graph with no slope or zero slope. Because here our rise is going to be 0 on this graph here. And so 0 over no matter how long we go, and here we did 5 seconds, is still going to give you a slope of 0. And the slope's actually going to be meters per second, which we will go into in a moment. So I'm not going to pause in these notes, but this would be a good time to pause to finish writing these down if you haven't already. And since my screen froze again, I guess I am kind of pausing. Okay, jumped ahead a few. So now what would a position time graph look like for an object that is stopped at 5 meters? So if you hear papers rustling in the background, this is me just following along in the notes that you have. So again, I would say pause and figure this out on your own. We'll do 1, 2, 3, 4, 5 seconds. And 1, 2, 3, 4, 5, 6, 7 meters. So if it's stopped at 5 meters, we know that at 0 seconds it's at 5 meters, at 1 second it's at 5 meters, and 2 seconds, and so on. And just like before, we can take a line and go right across. So now that we have our position time graph for this, what would our velocity time graph look like for an object that is stopped at 5 meters? So I suggest pausing it here and just trying this out on your own. And then once you've got an idea or an estimate or a guess, go ahead and hit play again. So I'm assuming you paused it, and now this is you hitting play again. So we know that if an object is going 0 meters per second, or if it's stopped, that means it's going 0 meters per second at 0 seconds. And the same for 1 second, and 2 seconds, and 3 seconds, and so on. So, and once again, we can just draw a line right through here. So this might be really intuitive for some of you. Some of you, this might be the first time you're seeing anything like this. So now what if we wanted to go from a velocity time graph to a position time graph? We're going to assume the x initial position is 0. This position here is actually talking about displacement, but position is fine for your label for our class. So now, if you remember from the previous section, we can actually stop at each of these points and see what the velocity is and add that up. So when we have a constant velocity, it makes it actually really easy from what we have seen before. So at 1 second, we know it's going 2 meters per second. So here, after 1 second, it will have gone 2 meters. Now at 2 seconds, it is still going 2 meters per second. So that being said, if you have 2 meters, a velocity of 2 meters per second, and you're multiplying it by 2 seconds, that's going to give you 4 meters. It's about here. And same thing for 3 seconds. It's still 2 meters per second. But now we're at 3 seconds. So we're at 6. And some of you have recognized the pattern by now. And once again, I can take a ruler and get a rough best fit line for this. Again, as freehanding, I got this a little off. You have graphing paper if you're following along with the guided notes. So hopefully your line looks a little bit better than mine does. So moving on, what if our object is not at a constant velocity? So what if the velocity is changing? What would that look like? So if our velocity is changing, and let's say it's accelerating, you're going to have a position time graph where it is growing faster than the time. So I'll let you copy this down. So a graph that looks like this would actually match a velocity time graph that looks something closer to this. So now we have a velocity that has a slope, and it is increasing over time. So this shows an object getting faster and faster as time goes on. So now we're going to find the slope the same way we did before, except now our rise is going to be our delta V, or our change in velocity. So that change in velocity over change in time will give us A, or acceleration. So our math model is going to look something like this. V final, and I'll get my little pointer out. V final equals acceleration times time plus your initial velocity. So, and this should look fairly similar to our previous formula for position, which was position is equal to, I want to keep the colors the same, velocity times time, oops, sorry about that, plus our position initial. This is actually our final position. So we're still using what would be called y equals mx plus b, but we're changing our slope for our velocity time graph is going to be acceleration, and our b is going to be our initial velocity. For a lot of the examples we go through today, the initial velocity or initial position if we use this formula is going to be 0. If it is not otherwise stated, you can assume it's 0. So it's important to note that the slope of a velocity time graph represents an object's acceleration. So an acceleration has a magnitude and a direction. So for those of you in my class, you should remember that that is a vector. Acceleration is the increase or decrease in the rate at which the object is traveling. So again, if an object is going a certain velocity and then it speeds up, in the same direction, the acceleration is positive with regards to that initial velocity. So, and we'll get more into it. If that doesn't make sense, just copy down what you see on the screen, and we will get more into it as we go. So remember, the units for this are going to be meters per second squared or meters per second per second. So, like we had before, our delta, our delta V over our delta T. Remember, our change in velocity is going to be in meters per second, and then our change in the change in time is going to be measured in seconds. And so that's how we get the meters per second. And if you divide this value by seconds, it can be simplified down to this formula, or units rather. So if we have an object that is traveling with a positive velocity, and if our acceleration is positive, then we can say our object is speeding up. So and that should be a little bit intuitive. So if I'm going in this direction and my acceleration is also in this direction, I should be getting faster. And remember, speeding up is going to be a scalar, not a vector. So we're just saying that it is speeding up in some direction. So that being said, if we have a positive velocity but a negative acceleration, then our object is going to be slowing down. So, and again, this should kind of make some intuitive sense. So if this is the original vector of how fast we were going, and you're accelerating in this direction, these arrows are going to get shorter as time goes on. If you think of like our motion map until you stop, and then you may even start going the opposite direction, having a velocity in the negative direction. And then you would start speeding up as long as your acceleration stays the same. So now that being said, if we have a negative velocity and a positive acceleration, you will still be slowing down. So, and in the same way, if we're going this direction, but our acceleration is going in this direction, these will become shorter over time until, again, you stop and then change direction. But if we have if we have a negative velocity and a negative acceleration, our object will be speeding up. And so this is just the change of direction of our first one here, where this one was positive and positive. So now it would be, your velocity is going in the negative, but so is your acceleration. Your acceleration should stay the same in this direction. So now these arrows for velocity should be getting longer. So the big thing to note here is if the velocity and acceleration have the same sign or direction, the object is going to be speeding up. Now, if they are opposite, though, the object is slowing down. So, and that's what we saw here. These ones here, these two here had the same direction for velocity and acceleration, whereas these two here had opposites, and so they were slowing down. So let's go through some practices here. So I want you guys to try this on your own first. Again, I'm not going to pause for very long here. So pause the video if you can and try and figure out these on your own first. I recommend pencil so that as we go through them, if you do need to change your answer, you can. So our time 0 is here. And our velocity is in this direction, and we can tell that the velocity is getting higher because these arrows are getting longer. So we already know that the velocity is in the positive direction, and since these arrows are getting longer, we also know that the acceleration is also in the positive direction, which means that our object is going to be speeding up. So now practice 2. Again, pause the video, try these on your own, or if you went through them all ahead of time and now are watching the video, then you don't need to pause. So now our velocity is still heading in this direction, so it's still in the positive, but we can see our arrows are getting shorter as time goes on until actually the object has stopped here. So our acceleration is actually in the negative, and since we have opposite directions for our acceleration and our velocity, our object is slowing down. And that kind of makes sense because you can see that it's going quite a bit of distance here, and then here it's completely stopped for 1 second. So here is our practice 3. So now our first second starts here, and you can tell right here we started from a stopped position. So then we have a velocity in this direction, which would make it in the negative direction. And once again, you can see that these arrows are getting longer in the negative direction. So our acceleration is negative, which means our object is speeding up. And so for our last practice for this, again, we start here. And we're definitely going into the negative direction here. So velocity is negative. Now we can tell that our arrows are getting shorter, which means our velocity must be working this direction, which means it must be positive. So our object is once again slowing down. So now with this practice, I'd like you to take a moment to try and graph these interactions on velocity time graphs. I will walk through the first one just because I think this is a new idea. So here at 0 seconds, from 0 to 1 second, we can see up here and you can see on your paper. the object was going 0 meters per second. Now here from 1 second to 2 seconds here, this arrow here represents the velocity at 1 second. So in that we can see it goes from 0 to 1 meters. And so that's going to put us at 1 meter per second at 1 second. So now in the same way, here's our 2 seconds is, let me change my color really quick. So our second is here, and this arrow here is its velocity, and it goes from 1 to 3. And if you don't have arrows that go all the way to the end, it is going to be the distance between the seconds is actually the full amount. I know that some practices we've seen have the arrows only going half the distance. It's really just a practice that some physicists use and teachers use. For us, we've been putting the arrows all the way to the next dot. So for this one, our second, it is going from 1 meter to 3 meters. So that is 2 meters in 1 second. So it'll be here. And some of you may have noticed the pattern, but if not, our 3 second is here. So from 3 to 4 seconds, it has gone from 3 to 6 meters. And so 3 to 6 meters means that it's going 3 meters per second. Again, I want to get my colors right. And now I know that this is linear because I've done this one. But so I'm going to make a guess here that this is going to be linear. And now our 4 second is here. And in this time it goes from 6 meters to 10 meters. So it's going about 4 meters per second. And that's about there. So I was right. Now we can't actually say what the velocity is at 5 meters because there was no arrow written there. You could say that it's going to continue with the same acceleration. And for this lesson, we are doing constant acceleration. But it could just as easily turn around here or start slowing down. So you can't actually say what is happening at this 5 second mark. So you should have your arrow end or your line end back here. All right, now that we've walked through the first one, I want to give you a second to pause and work through the rest of them. So pause the video here and work through making a graph of motion maps 2, 3, and 4. If you get stuck, absolutely come back and watch the videos. But I'm going to just pause here. So hopefully now, if you are still playing or hit play, you have tried these on your own. So now for this motion map, we know that at 0 seconds, we're at 0 meters. And the arrow here has gone to 1 second, has gone 4 meters in 1 second. So we know at 0 seconds, our object is going 4 meters per second. So now this is our 1 second and our 2 second. So now the distance between these two is 3 meters, and that's going to be at the 1 second, because again, this arrow represents what's happening at this dot. oh, sorry, okay. This dot here, this arrow is what represents that. So we know at 1 second it is 3 meters per second, and at 2 seconds here, this arrow is going from 7, 8 to 9, so that's going to be 2 meters. And then from seconds 3, oh, and there should have been a little arrow there. So from seconds 3 to 4, it goes 1 meter. So at 3 seconds, it's going 1 meter per second. And now we know from 4 to 5, it actually doesn't move anymore. So the velocity is going to be 0. And once again, we'll have a best fit line. Hopefully, again, yours are a little bit cleaner than where my dots are, but it should fall right on that line. So now we're going to do the same thing with this motion map. Again, if you haven't done it, pause here. But otherwise, so now we're going to be starting at 10 meters for our initial time. So between 0 seconds and 1 second, our object doesn't move, so its velocity is going to be 0. Now I know this one's tricky because you want to start it in the negative, but remember we're graphing the velocity, not the position. So it is going to start at 0. Now here is 1 and 2, or you might have wanted to start it at positive 10 up here, but again, we're doing the position, or we're doing the velocity, not the position. So now at 1 second, you have this distance here, and so it's going in the negative direction, and we're going from 10 to 9, so we can say it's about -1 at 1 second. And again, we should be able to see the pattern here. This is 2 meters here, so at 2 seconds it's at 2 meters. Here it is 3 meters at 3 seconds, and 4 meters at 4 seconds. And again, get a nice little line. And once again, at our 5 second mark, we cannot say what the velocity is, so we're actually going to just stop right here. And for this last one, I'm just going to give you the answer. Again, you should have tried it on your own. So that is 5 meters at 0 seconds. Oops, I'm sorry, it is 4 meters. -4 meters, because we're going from 10 to 6. And then we're going from 6 to 3, which is 3 meters. And from 3 to 1 is 2 meters per second. And from 3 to 4 is 1 meter. And I think in your example there is another dot here, so we can say that it goes down to 0 meters per second at 4 seconds. And again, we can't go any farther than that because we don't know what happens from that 5th second and so on. So now you should have a pretty good idea of how to graph a velocity time, a graph from a motion map. But now what if we have a velocity time graph and we wanted to find its displacement? And in turn be able to go back to a motion map. So we're just going to look at how to find the displacement. So your first example on the notes should look something like this. And I'm actually going to move this up just a hair so it looks more like yours. Now, our first thing is we need to find our formula for displacement, and we actually were using it before, and I brought it up earlier. Our formula for displacement, if you remember from previous sections, is delta x is equal to velocity times time. So now our velocity here with a constant velocity time graph is really easy. It's going to be 5 all the way across. So for our velocity, we're just using this distance here, which is 5, from 5 to 0, meters per second. And then our time is going to be, we start at 0 and go to 6 seconds. And that is going to be equal to our delta x, which incidentally is going to be the same volume that you would find if you thought of this as a rectangle. So if you think of this length as 6 and this height as 5 meters per second, that would give you the same answer for your delta x, which is equal to 30 meters. Which, again, you can mathematically check of if you're going 5 meters per second for 6 seconds, which is what we did here, you'd get 30 meters. And if you're doing this on graph paper, you can actually count out these boxes. So 1, 2, 3, 4, 5. And you can do that for each second. I'm not going to do it because it takes too much time. And we have this nice little math formula here. So once again, this is going to be our change in velocity, or our velocity. Here it's a constant velocity, and this is our change in time. So I had these notes written out ahead of time, I forgot. So you get to see them twice. And this should have a units. All right. So now for our example 2, we have a line that's down here. And in the same way, we're still going to have, you're still trying to find this area, but displacement has a direction. And we're working in the negative here. So our velocity is -5 meters per second. And our time this time is going to be 10 seconds. So, and that will be equal to our delta x. And so our delta x is going to be equal to -50 meters. So again, if you have any questions about how we got that, we're still using this formula from before, which is our position and time. Our position given that we have a velocity and time. So now take a moment and try and figure out what our displacement would be from this graph. I will give you a hint that I recommend you split these up into 2 different and then add them together. So take a moment to pause here and then we will get started. Alright, so if you've paused and hit play again, you should have found that this one here, you went 5 meters per per second for 5 seconds, which would give you a positive 25 meters. Whereas this one, on the other hand, is going to give you negative 5 meters per second. And again, from 5 to 10 is going to be another 5 seconds. So 5 seconds. And that is going to give you negative 25 meters. So now this is our delta x1 is equal to positive 25 meters. Our delta x2, saying this is x1, x2, is equal to negative 25 meters. So our delta x total is going to equal, well, 0 meters. Because 25 plus negative 25 is going to get you that. So, and this might look like an object that is going 5 meters per second this way, and then turns around, and ends up right back at the starting point. So now for the last one, again, we're still trying to find the area underneath this. So I'll again pause for a moment, try and figure it out for yourself. But in just a minute we'll go through it. So we know that the formula for a triangle, or we can see that this is just going to be half. You're going to have half of the velocity times the time. So now our delta x is going to equal 1/2. And so our velocity here, if we had made this a full square, would be 6 meters per second. And our time from here to here is also 6 meters, or excuse me, 6 seconds. Ooh, I'm getting tired. So now if you multiply all those together, 6 times 6 is 36, times 1/2 or 0.5 is going to give you 18 meters. And again, if you don't believe me, feel free to count up all of these squares. It ends up being 18 meters. So now I really want you to try this last one. If you haven't been trying, I know that sometimes it's just easier to watch these. But you will have a quiz on this and a test coming up. So really try this one. This one is kind of a combination of all the things we've been talking about. You should, if you've been working along with this the whole way, be able to do this one. But again, pause here. Okay, so hopefully you paused and hopefully you found out an answer. Like we did in one of the previous ones, up here are number 2. I'm going to have you split this up into 2 different portions. So this is at 2, and it's easier to see on your graph. It should be a little more clear. I don't have grid lines on mine. So I'm going to break this up as x1, and this is going to be x2. So I'm going to move this, move this. So now our delta x1 is going to equal, remember we said 1/2 because that's the formula for a triangle. 1/2 of the height, which is from 2 to 4. Our 2 to 4 is going to be 2 meters. 4 meters per second minus 2 meters per second. A little bit more room. And our time is going to be from 0 to 6. So 6 minus 0 is going to just give us 0 seconds. And this here is 4 minus 2 is going to just give us 2 meters per second. And so 2 times 6 is 12 times 0.5. We are back to 6 meters. So delta x1 is equal to 6 meters. Now delta x2 is just a regular rectangle. So we can just do the height, which is from 0 to 2. So 2 meters per second times our time, which is still 6 seconds. And that will give us a delta x2, or a change in position 2 for this part, as 12 meters. So now add those up. Delta x total is going to equal 12 plus 6, which would give us 18 meters. So hopefully that made sense on how we did that and how we walked through it. If you're in my class, feel free to ask questions. I'm available before and after school, and at lunch. I'm also accessible via email or Remind. Yeah, but real quick before we go, I want to go over what we went over. So we had all of these notes, and we were able to go over. We reviewed our position time graphing from last unit. We learned how to graph constant and changing velocities. We defined acceleration. We practiced identifying acceleration from motion maps. We practiced graphing changing velocities. And we found displacement from a velocity time graph. So hopefully you're masters at this now, and if you are in my class, you should already have the practice for this section. If you are not in my class and you just stumbled upon this video, I should have that in the links below, or in the comment section below. So anyway, thank you, and hopefully this was worth your time.